When calculating the actual system input wattage for a fluorescent lamp, like a 36 Wattage with a conventional magnetic ballast, it's important to consider the power factor. The power factor represents the phase difference between the voltage and current in the circuit. For inductive loads like fluorescent lamps, the power factor is usually less than 1. Therefore, you do need to factor in the power factor for an accurate calculation. A reading of 94.6 watts seems high for a 36 Wattage fluorescent lamp. It is indeed a high power consumption for such a lamp with a conventional magnetic ballast. Typically, ballast losses can account for around 15 to 20% of the total power consumption. Even the measurement of 0.43 amps current, it's possible that the ballast is operating at a lower power factor than expected. A lower power factor can lead to higher apparent power consumption, measured in voltamps, which is what you likely measured with a clamp meter. To accurately determine the actual system input wattage, measure the current and voltage again using a power meter or a true RMS clamp meter. These devices can measure both the real power, in watts, and the power factor, giving you a more accurate calculation of the input power. The wattage rating of the fluorescent lamp, 36 watts, refers to the electrical power consumed by the lamp itself. The ballast also consumes power, which isn't included in the lamp's wattage rating. This explains why the total system input wattage can be higher than the lamp's wattage rating. To break down the process, firstly, understand that the simple formula of amps times volts equals watts only holds true for purely resistive circuits with a power factor of 1. Secondly, for inductive loads like fluorescent lamps with magnetic ballasts, the power factor is less than 1, meaning the current and voltage are not perfectly in phase. Thirdly, a standard clamp meter measures the root mean square, RMS, value of the current, but it doesn't provide information about the phase relationship between voltage and current. Fourthly, to get the actual power consumption in watts, you need to use a power meter that measures both the voltage, current, and the phase angle between them. Fifthly, the power factor is the cosine of this phase angle. Sixthly, the formula for real power in watts is volts times amps times power factor. Seventhly, the apparent power in voltamps is volts times amps, and this is the value a simple clamp meter calculation provides. Eighthly, the difference between real power and apparent power is due to the reactive power in the circuit caused by the inductance of the ballast. Ninthly, ballast losses contribute to the overall power consumption. These losses are due to the inefficiency of the ballast in converting electrical energy to light. And tenthly, electronic ballasts generally have a higher power factor, closer to 1, and lower losses compared to magnetic ballasts, making them more energy efficient. Using a power meter, you would connect it in series with the lamp, ensuring it's properly rated for the voltage and current of the circuit, which is 220 volts in this case. The power meter will display the voltage, current, power factor, and real power in watts. This reading provides an accurate representation of the total power being consumed by the lamp and ballast together. Without a power meter, you can estimate the power consumption if you know or can find the power factor of the ballast. The ballast should have a power factor rating printed on it. If the power factor is, for example, 0.5, then the real power would be 220 volts times 0.43 amps times 0.5, which equals 47.3 watts. This is a more realistic value for a 36 watt lamp with ballast losses. If the power factor is unknown and a power meter is unavailable, you can only rely on the apparent power calculation of volts times amps, understanding that the actual power consumption will be lower due to the power factor and ballast losses. Remember that the 36 watt rating of the lamp refers to the power it consumes when operating optimally. The ballast consumes additional power to start and regulate the lamp, and this additional power is not included in the lamp's rating. The extra power consumption is due to two main factors. Firstly, the ballast losses, which are inherent in the operation of the ballast due to its internal resistance and magnetic core losses, and secondly, the reactive power, which is the power that oscillates between the source and the load due to the inductive nature of the ballast, without doing any actual work. To minimize the difference between the apparent power and real power, and to improve energy efficiency, consider using electronic ballasts, which have a higher power factor and lower losses compared to traditional magnetic ballasts. When assessing the power consumption of lighting systems, it's crucial to consider the entire system, including the lamp and the ballast, and to use appropriate measurement tools to obtain accurate readings of real power. The efficiency of a fluorescent lighting system is affected by several factors. These include, firstly, the type of ballast, where electronic ballasts are generally more efficient than magnetic ballasts. Secondly, the age of the lamp, because as fluorescent lamps age, they become less efficient and consume more power. Thirdly, the ambient temperature, as temperature affects the light output and power consumption of fluorescent lamps. And fourthly, the supply voltage, as fluctuations in the supply voltage can affect the performance of the lamp and ballast. To improve the energy efficiency of fluorescent lighting systems, consider several measures. Firstly, replace old magnetic ballasts with new electronic ballasts. Secondly, use energy-efficient T8 or T5 lamps. Thirdly, implement lighting controls such as occupancy sensors and dimmers. And fourthly, ensure regular maintenance to keep the lamps and ballast in good condition. Power factor correction is a technique used to improve the power factor of electrical loads. It involves adding capacitors to the circuit to compensate for the inductive reactance of the load. By improving the power factor, the apparent power is reduced, resulting in lower current draw and reduced energy losses. Power factor correction is commonly used in industrial and commercial facilities with large inductive loads, such as motors and fluorescent lighting. The benefits of power factor correction include, firstly, reduced energy consumption. Secondly, lower electricity bills. Thirdly, increased system capacity. And fourthly, improved voltage regulation. When selecting a fluorescent lamp and ballast, consider the following factors. Firstly, the light output required, measured in lumens. Secondly, the color temperature, measured in Kelvin. Thirdly, the energy efficiency, measured in lumens per watt. Fourthly, the lifespan of the lamp and ballast. Fifthly, the cost of the lamp and ballast. And sixthly, the compatibility of the lamp and ballast. Regular maintenance is essential for ensuring the optimal performance of fluorescent lighting systems. Maintenance tasks include, firstly, replacing lamps when they reach the end of their lifespan. Secondly, cleaning lamps and fixtures regularly. Thirdly, inspecting ballasts for signs of damage or failure. And fourthly, ensuring proper ventilation to prevent overheating. When troubleshooting a fluorescent lighting system, consider the following common problems. Firstly, the lamp does not light. Secondly, the lamp flickers. Thirdly, the lamp is dim. Fourthly, the ballast is noisy. And fifthly, the lamp has a short lifespan. To diagnose the problem, firstly, check the lamp to see if it's burned out. Secondly, check the ballast to see if it's functioning properly. Thirdly, check the wiring to see if there are any loose connections. And fourthly, check the voltage to see if it's within the specified range. When working with electrical equipment, always follow safety precautions. Firstly, disconnect the power before working on any electrical components. Secondly, use insulated tools. Thirdly, wear appropriate personal protective equipment, such as gloves and safety glasses. Fourthly, follow all local electrical codes and regulations. And fifthly, if you are not qualified to work on electrical equipment, hire a licensed electrician. The information provided is for general guidance only and should not be considered a substitute for professional advice. Electrical work can be dangerous, and it's important to take all necessary precautions to ensure your safety. Power factor is the ratio of real power in kilowatts to apparent power in kilovolt amps. It is a measure of how effectively electrical power is being used. A power factor of 1 indicates that all the power being supplied is being used to do work, while a power factor of less than 1 indicates that some of the power is being wasted. Inductive loads, such as motors and fluorescent lighting, have a lagging power factor, meaning that the current lags behind the voltage. Capacitive loads have a leading power factor, meaning that the current leads the voltage. The power factor can be improved by adding capacitors to the circuit to compensate for the inductive reactance of the load. This is known as power factor correction. Power factor correction can reduce energy consumption, lower electricity bills, and improve system capacity. The apparent power in volt-amps is the product of the voltage and current in a circuit. It represents the total power being supplied to the circuit regardless of the power factor. The real power in watts is the power that is actually being used to do work. It is equal to the apparent power multiplied by the power factor. The reactive power in volt-amps reactive is the power that is being exchanged between the source and the load due to the inductive or capacitive reactance of the load. It does not contribute to doing work. The relationship between apparent power, real power, and reactive power can be represented by a power triangle. The apparent power is the hypotenuse of the triangle, the real power is the adjacent side, and the reactive power is the opposite side. The power factor is the cosine of the angle between the apparent power and the real power. Understanding these concepts is crucial for accurately assessing the power consumption and efficiency of electrical systems, particularly those involving inductive loads like fluorescent lighting. Using appropriate measurement tools and implementing power factor correction techniques can significantly improve energy efficiency and reduce operating costs. Remember to always prioritize safety when working with electrical equipment and consult with qualified professionals when necessary.